Okay, we are going to get started. Welcome to the Center for Biodiversity Conservation Science seminar series. Today we are very excited to have one of our own, Dr. Wilma Blaser Hart, and she will be giving us a talk about cacao, which is something that her being Swiss and growing up in the capital of chocolate, which is Zurich and Geneva, probably has. Is that where your love of cacao came from? Probably. And then Wilma did her PhD at ETH Zurich, which is one of the top 10 universities in the world, where she worked on a variety of things, but didn't really get into cacao specifically until a bit later. Is that correct? And now, not only does she work on cacao, study it, but she's also involved in the organizations that govern how cacao and sustainability credits or certifications are being done. So really working on the research side and the application and applied side. So my pleasure to introduce her. But before we get started, I would like to acknowledge, do an acknowledgement of country. The University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors, their descendants, who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. With that, welcome, Wilma.
Okay, because we had some technical problems over this morning, and she did that with us, so thanks a lot. Yeah, so as Matt already said, today is all about cocoa and the key ingredient of chocolate, but it's also going to be about so much more than just chocolate. It's about how we can reconcile agricultural production with climate change mitigation and biodiversity conservation. So there's huge sustainability challenges for cocoa production around the world, but these challenges are particularly acute in West Africa, where we have about 65% of the global production of cocoa that's coming from. Cocoa production in West Africa is threatened by aging plantations, decreasing soil fertility, increasing levels of pests and diseases, and combined these lead to low productivity. And instead of increasing the productivity of existing farms, farmers often tend to increase cocoa production by expanding the area on which cocoa is produced. And this is leading to massive deforestation, which large impacts for the climate and for the remaining biodiversity. Just to show you how extensive that is, we made some maps of cocoa growing areas across Ghana and Ivory Coast. So in this map here, you see everything that is hashed in red is a protected area. Everything in black is not cocoa, so it could be forest, could be a village, and everything that's cocoa is in white. So this is Cocoa National Park, a national park in Ghana, where we currently do some work, and you see that everything inside this protected area is black, meaning forest protection here is working well. Fortunately, this is not looking so well in other protected areas, such as these two examples shows where you can see that entire protected areas have just been converted to white areas, which means there's just cocoa growing there, there's no forest left. And in this study, we estimate that across the Ivory Coast, with about 37% of the forest loss that was driven by cocoa, and in Ghana, this number is about 13% of the forest loss that was driven by cocoa expansion. So cocoa is really a big driver of deforestation in these two countries. And to make things worse, future cocoa production is threatened by climate change. So we really have quite a few challenges that are going on in the cocoa sector. And integrating trees in cocoa systems could be a way to help with these challenges, because agroforestry systems are perceived to have many benefits. They could help farmers adapt to climate change by buffering temperatures and humidity. They could help us mitigate climate change by sequestering carbon both in the above and below ground biomass and in soils. And they can also provide habitat for rich flora and fauna, and thereby contribute to biodiversity conservation. And then overall, they can help to sustainably increase agricultural production by helping to increase or maintain soil fertility, have buffering effects on pests and diseases, and they can also provide alternative products that can help to improve farmer livelihoods. So overall, there's really huge benefits that these agroforestry systems could provide, but we also don't really know how big these benefits really are. So this is why we did a global meta-analysis trying to pull out all the information that looks at how big the impact of adding shade trees to these ecosystems really is. And we found 48 studies that directly compared shaded and unshaded systems. And within these studies, there's 134 comparisons of shaded versus unshaded systems. So what we did is we calculated the difference between what was reported for shaded and unshaded. And I'm now going to show you a series of results that always shows this difference for different parameters. So if we have increased values under shade, this is going to be shown as positive values. Decreased values under shade relative to unshaded systems is shown as negative values. And I'm going to highlight benefits of agroforestry in blue and costs in red to be able to pull all that information together. So the first thing we looked at was climate change adaptation. And there we find that shaded systems indeed buffered temperatures. That's not really surprising, but it's still good to have that confirmed. So that's a benefit of having agroforestry systems. And with respect to climate change mitigation, we found that soil carbon stocks were increased, but this was not significant. But we found significantly higher above ground carbon stocks in the above ground plants. So again, this is a huge benefit of adding shade trees to these ecosystems for climate change mitigation. The next thing we looked at was biodiversity conservation. And here we found information on several taxa, which we all lumped together here just to have an overall number. And we did find that species richness was significantly increased under shaded systems across several taxa. And then we also looked at impacts on diseases and disease incidences. And we found that the results there were a little bit mixed. And we only found information on fungal diseases. So we had higher infestation rates of frosty spot diseases, but this was not significant. Higher infestation rate of black spot disease, which is what we commonly find in West Africa. That looks like it's almost at zero, but it was actually significant. And then negative effects on Woodgerspoon disease, which is a disease that we only found in South America. And so overall, we have a cost for some fungal diseases, but then a benefit for others. But overall, it looks like the benefits are like sort of only present. But if we add shade trees to cocoa systems, these trees also compete with the crop for light water nutrients. And so if we have this much yield in a monoculture in a shaded system, we're likely to have a little bit less yield due to this competition. And this is what we found across our analysis, where across these 48 studies, most studies reported that cocoa yields were actually lower in shaded systems. So it's the cost of adding trees. So overall, we have quite a few benefits, but we also have some cost of adding trees. But does that then mean that we can't really have any of the benefits without a cost for production? Or are there ways to maximize these benefits while minimizing the cost for production? And the costs and benefits are likely to be mediated by the level of shade, because as we add more and more shade trees, we're likely to have bigger competitive effects between the trees and the crop. But as we add more and more shade trees, we're also likely to have bigger benefits, such as the buffering effects of temperature, for example. So this is why in a study that we did in Ghana, we looked at a grading of increasing shade tree cover to try and work out how much shade we should add to these cocoa systems to maximize these benefits while minimizing the costs. And so in a cocoa landscape, like shown here from an aerial picture, we selected plots that had shade trees, and then we paired them with nearby monoculture areas that didn't contain any shade trees. And these pair plots were selected along a gradient of increasing shade tree. The pairing was done so that we could isolate the effect of trees from other confounding variables, such as different flower management, differences in soil, in soils, differences in microclimate, for example. And then in all these plots, we measured a range of variables related to climate change adaptation, climate change mitigation, biodiversity conservation, and agricultural production to look at the trade-offs and then work out what best to cover. So I'm now going to show you a series of results again, and similar to the results that I've shown you from the meta-analysis, but instead of just showing one dot, you're gonna have lots of dots along a gradient of increasing shade tree cover. And we didn't calculate the absolute difference, we calculated the relative percentage difference. But again, if you have higher values under shade, this is shown as positive percentage differences. Lower values under shade is shown as negative percentage differences. Benefits are again shown in blue and costs are shown in red. So with climate change adaptation, we expect that the trees would buffer temperatures, and they did so, and they did increasingly so with decreasing shade tree cover. So this is an increasingly big benefit as we add more and more trees. And then for soil moisture, we found that trees did compete with cocoa for soil moisture, but only at high shade densities. For above ground, for climate change mitigation, we found that trees increase the carbon in these systems in the above ground biomass, but not in soils. So again, we have an increasingly big benefit. Same was for biodiversity conservation, where we had higher bird richness as shade tree cover increased. We also found similar results for frog and ant richness, but the relationship was less strong. And then for agricultural production, we looked at two things. We looked at losses to diseases, which were minimized at intermediate shade levels. And we also looked at cocoa production, and cocoa yields were actually maintained up to a level of about 30% and then started to decrease when shade tree cover got excessive. And so using all these colors, we can pull this information together and we can see that there's clear trade-offs between costs and the benefits of agroforestry systems. And if we now were to sort of determine what kind of shade level we would recommend, we can say that between 30 and 40% cover would allow us to not yet have losses to yields, but would already give us positive benefits for buffering disease levels, buffering temperatures, have higher carbon stocks, and have higher biodiversity or high species richness. And so this is why, based on this, we recommend that we would implement agroforestry systems with shade levels between 30 to 40%. But if we were to use these recommendations elsewhere, other than where we did our study, we would have to make some adjustments, because it could be that the climate is slightly different, so that might shift this a little bit. It could be that farmers manage their farms. So for example, if they prune their farms well, there could be less self-shading on the cocoa, which might mean that they tolerate shade. It could be that these agroforestry systems provide alternative products, which could increase farmers' income, so they might be able to tolerate a bit of a loss in yield because they get compensated for this loss by other products. Or it could be that the careful selection of shade tree species can also allow us to bring in more trees that would have less shade for even carbon, for example, that could allow us to shift this balance a little bit more. And then ultimately, it also really depends on what our goal is, because if we want to maximize production, we would go with this 30 to 40% recommendation. But if we want to maximize carbon stocks or biodiversity conservation, we would not really go for a system that has still that much low shade. But then there's sort of bigger landscape questions that we need to ask if we start to have systems that agricultural systems that we want to maximize for carbon stocks or biodiversity. But nevertheless, regardless of how we slightly shift this recommendation towards a little bit more, a little bit less shade, we see that there's emerging recommendations across all cocoa growing regions that say somewhere between 30 to 50% shade will be good for cocoa systems, because we do not yet have a reduction in yields. And this is why cocoa agroforestry has been increasingly promoted by the cocoa sector. Since 2018, there's about 43 million shade trees that have been planted under the Cocoa Forest Initiative, which is a multi-stakeholder initiative of the cocoa sector that involves both cocoa traders, chocolate producers, but also the governments of Ivory Coast and Ghana. And so this is a hugely positive initiative, but there are some technical limitations and knowledge gaps when it comes to planting millions of shade trees, because we don't really know where we already have agroforestry systems and where we should target our interventions. And we don't really know what the current carbon stocks are in these systems and just how much extra carbon could be brought into these systems if we implemented agroforestry systems at scale. And then the industry also lacks efficient, cost-effective tools to monitor their agroforestry interventions. And so this is why our most recent project looked at developing methods to determine shade recovery and carbon stocks in cocoa systems. And to do this, we developed machine learning models that can map Sentinel-2 images, which are satellite images at a resolution of 10 by 10 meters, to estimates of shade tree cover. And we trained this model using ground truth data that we collected using drones. And we then used this model that we developed to make a map of shade tree cover across all cocoa growing areas across Côte d'Ivoire and Ghana. So in this map here, everything that has a color is part of the cocoa growing area. That's about more than 7 million hectares of land, which is more than 10% of the area of each country. And the colors show the levels of shade. And you can see that there's no yellow that you can visually detect. So there's really everything is below 30% shade tree cover. And on average, these shade levels are about 13%. And there's only, if you count every pixel, there's about 5.6% of the entire map that has shade levels above 30%, which is also shown in this histogram that just shows the distribution, like all the pixels in the map where they fall along this shade cover percentage. So really not much shade in these systems. And then we also made a map of above ground biomass density. For this, we used deep learning that was trained on JEDI footprints. And in this map, you can see everything with high above ground biomass density in light green and yellow hues, and everything that has low density in dark blue hues. And we can easily convert this map of above ground biomass density to a map of carbon stocks. And this is what we then used, because we used the pixel level estimates of shade tree cover and the pixel level estimates of carbon stocks to look at the relationship between shade tree cover and carbon stocks. Using this, we could then make predictions on the climate mitigation potential of implementing agroforestry across Ghana and the Ivory Coast at scale. And so at the moment, we have 118 million tons of carbon that's stored in these cocoa systems, so in these 7 million hectares. But if we increase shade levels to a minimum of 15%, which is in line with the definition of forests for Ghana and also the cutoff for lots of the Red Plus projects, we could add an additional 17 million tons of carbon to the systems. But the added carbon will be a lot bigger if we were more ambitious and followed the recommendations and added a minimum of 30% shade tree cover to these systems. So that would add 84 million tons of carbon to these systems, which would be enough to counterbalance about 10% of the annual greenhouse gas emissions of these two countries combined for the next 30 years as trees mature. So it's quite a bit of carbon that we could sequester in these systems. However, these 84 million tons are only almost equivalent to the carbon that's still stored in the intact forest. So that just emphasizes that we could do a lot with adding trees to cocoa systems, but we can do so much more by protecting the forest that's already there. And so you see that there's a lot of unrealized potential for climate change mitigation. But I mentioned that there's 43 million shade trees that have been distributed. So I just want to quickly explore what we've already achieved of that potential, because these trees that have been distributed, they cannot yet be seen in our maps because there's only just planted, they're not yet big enough to be protected. We calculate that if these trees were actually planted, they would only cover about 11% of this entire cocoa growing area. And if they matured, they would only reach shade levels from an average of 13 to an average of about 15 to 16%. So they would, it sounds like a lot, these 43 million, but it would really only shift the needle a little bit when we look at average shade tree covers. And as we've seen, that shifting from 13 to 15% would already have quite a bit of impact for climate change mitigation. it leaves us to wonder what this would mean for biodiversity and if it would mean anything at all. So going back to the relationship of shade tree cover and bird species richness, here it's not shown as a difference, it's just plotted the absolute numbers from the gradient study that I've shown you before. We can see that if we increase shade levels to 15%, this is really not going to make the most out of what these agroforestry systems could do for biodiversity conservation. So we were actually interested, and this is work we did with an honor student, Rachel Drimmel, and we are plans to really work that up this year and then publish it. And we looked at how many, like which birds actually overlap with the cocoa growing area and could benefit from annual trees. And we found that there's 178 forest dependent trees in Ghana, and 94% of them overlap at least to some degree with cocoa growing areas. So these cocoa growing areas could really be bird habitat if they were done, if they had habitat structure that could suit these birds. But we also ordered the birds according to their habitat requirement, and this was done roughly based on information from the ALNet. But we can see that most of these birds have high shade requirements, and we classified this as having about more than 60% shade tree cover. About 20% of all birds would need medium shade tree cover, so this would be like 30% and a little bit more, and only very few have low shade requirements. So at the moment, with our 13% shade tree cover, we really don't provide much habitat for these forest dependent birds at all. And even if we shifted it to 15%, this is not really going to have a huge impact for biodiversity. So again, this makes it even more important that we protect the remaining forest. But then if we had another 43 million trees to plant, would there be a way to actually get much more out of planting these additional trees? And this is not just hypothetical, because the Copeland Forest Initiative is actually going into a new phase. So there will be more trees that these people are planting. And so this is why, again, with Rachel, we used conservation planning to see if we could use this extra planting to really protect the habitat for these birds. So we set the conservation target to protecting a minimum of 30% of the range of all forest dependent birds. The visual isn't great, so don't worry, it's just there. We use conservation planning. Well, that's what we need to improve for the publication. But what we find is that the conservation target can be met only if we protect all intact forests, and in addition, restore some of the degraded forests. And cocoa is actually a big part of the solution, because we can only reach the target if we use targeted tree planting in some cocoa areas. About 5% of the entire cocoa area would need to have trees with we need to have systems that have more than 60% shade tree cover. So it's really small part of the area. 43 million trees should be enough to do that, but it really only works if we plant them in targeted way to support these forest dependent birds. So I hope that overall I was able to show you that there's huge benefits that the planting trees in agroforestry systems could provide for climate change mitigation, climate change adaptation, for biodiversity conservation, also for buffering effect on pests and diseases, and most importantly, that a lot of this can already be achieved without a cost yield. But a lot of this potential remains unrealized across Ghana and the Ivory Coast. And so tree planting at its most basic level would already give us some benefits, but more targeted tree planting, like I've just shown you before for bird conservation, would really get a long way towards contributing to the conservation of forests and birds in Ghana. So that's all from my side today. I'll be happy to answer any